Today we begin our discussion of exponential functions. The exponential function I'm going to use is f of x equals 3 raised to the x power. You should notice that for an exponential function, the independent variable x is an exponent, and we always have some base. In this case, it is base 3. And if we begin to graph this, 3 to the 0 power, well, anything to the 0 power is 1. 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27, which is already off the page. You'll notice that there is very rapid growth here. 3 to the fourth power would be 81. 3 to the fifth power would be 243. We're moving very rapidly. If I look on as negative exponents, 3 to the negative first is 1/3. 3 to the negative second is 1/9. 3 to the negative third is 1/27. And no matter what power I take over here, the value of 3 to the x is just going to get smaller and smaller, but never become 0. So what I have is, I have rapid growth over here, and I have approaching a horizontal asymptote over here, which I could even show in yellow. Okay, so what is the domain of this exponential function? The domain appears to be all real numbers, so negative infinity to infinity. The range, 0, not including 0, to infinity. The y-intercept, 0, 1. And we definitely have a horizontal asymptote. It's kind of a half horizontal asymptote, but it is at y equals 0. So this is an exponential function. It's showing growth. In fact, it's showing, based on this base of 3, that my values are tripling as I go forward. And as I go backward, I'm ending up with 1/3 of what I had before. So we have, you could think about it as very slow growth and then very rapid growth, or you could think about it as rapid growth over here and a slow decline over here, but never ending up with nothing. So let's try to transform this. Let's do f of x minus 2, which would mean 3 to the x minus 2. That means every point on the original graph will move down 2. So the point at 1 will move down 2. 1, 3 was the original point, so it will move down 2. 2, 9. 4, 6, 8, 9 will move down 2. Negative 1, 1/3 will move down 2. Negative 2, 1/9 will move down 2. So, and so will my asymptote, which was at 0. Now it's going to move down 2. So what I have is the same graph I had before, only it is shifted down 2, which means the range is now negative 2 to infinity. The y-intercept is now negative 1, pardon me, 0, negative 1. And the horizontal asymptote is now at y equals negative 2. What if we did negative f of x, which means negative 2 raised to the x? This, we know, is a reflection over the x-axis. Order of operations, we know that the exponent will go first, and then we're going to tag a negative onto our answer. Because the original graph was all above the x-axis, this graph is going to be entirely below the x-axis. So the point at 0, 1 is now at 0, negative 1. The point at 1, 3 is now at 1, negative 3. The point at 2, 9 is now at 2, negative 9. The point at negative 1, 1/3, negative 1, negative 1/3, negative 2, negative 1/9. My horizontal asymptote, which was at y equals 0, is still at y equals 0. And my graph is now going this way. So my range is now negative infinity to 0. My y-intercept is now 0, negative 1. And my horizontal asymptote is at y equals 0. E to the x. E is a number like pi. It's an irrational number, but it is well defined. I'll show it to you on our calculator. If I do the second function of divide, that's e, and if I hit enter, it will show you that e is about 2.718, which means it's close to 3. So this graph is going to look like 3 to the x, only it's going to be growing a little slower. The base e is for things that grow naturally. So natural growth is represented by E. So populations, germs, a new species in a habitat, that kind of stuff. Bacteria grows naturally. So it's going to have base E as its growth base. Also, things that grow continuously. So anything that grows continuously. So you can have various applications that all have E in it. If I put this in as a function, I'm going to use a different E. I'm going to use the E that's the second function of natural log, because it assumes, second function of natural log. It assumes I'm going to put a power on that, so I'm going to put x as my power. I want to look at my table. Notice that for small powers, I get for negative powers, I get small values. For 0, I still get 1. For 1, I get 2.7. For 2, I get 7.3891. So that's close to 9. For 3, I get 20. Base 3 would have 327. So we are growing slightly slower than 3 to the x. But if I were to make a sketch of this, which is about all I really want to do here, what I would notice is that anything to the 0 power is still 1. I'm coming toward a horizontal asymptote over here. I'm doing some growth over here. So my range, 0 to infinity. My y-intercept, 0, 1. My horizontal asymptote, y equals 0. If I use a base that's smaller than 1, like 1/4 raised to the x, I get, instead of growth, I get decay. And for some things, like cars, iPads, we use the word depreciation because they're losing value. If I were to graph this, one-fourth to the 0 power is 1, because anything to the 0 power is 1. 1/4 to the first power is 1/4. 1/4 to the second power is 1/16. 1/4 to the third power is 1/64. So we're getting that sort of losing a value but never becoming nothing. 1/4 to the negative first power is 4. 1/4 to the negative second power would be 16. 2, 4, 8, 10, 12, 14, 16, 8, 10, 12, 14, 16. Okay. In case you want to see that, 1/4 to the negative second power would be the reciprocal of 1/4, so 4 to the second power. Or maybe you're seeing it as 1 to the negative second over 4 to the negative second, which would be 4 squared over 1 squared. I'm not sure how you process your negative exponents. There are lots of ways to do that. But in any case, it is 16. So what we get is we get our horizontal asymptote over here. This is the side that's going to infinity, and this is the side that is approaching the horizontal asymptote. So what we have with exponential decay or depreciation, the feel of the graph is that initially there are big losses in value, huge losses in value. But what you're losing less every single time, and so you never end up with nothing. So this space would say, every time I go forward, I have 1/4 of what I had before. And I will always have something left to take 1/4 away from. So I have 1/4 of what I had. Actually, I'm taking 3/4 of it away if I have 1/4 left. Okay, so that's what we've got for today. Watch this as many times as you need to.